Graphical models. Graphical models represent the interaction between variables visually and have the advantage that interference over a large number of variables can be decomposed into a set of local calculations involving a small number of variables making use of conditional independencies. After some examples of inference by hand, we discuss the concept of D-separation and the belief propagation algorithm on a variety of graphs. Introduction. Graphical models, also called Bayesian networks, belief networks, or probabilistic networks, are composed of nodes and arcs between the nodes. Each node corresponds to a random variable x and has a value corresponding to the probability of the random variable p of x. If there is a direct arc from node x to node y, this indicates that x has a direct influence on y. This influence is specified by the conditional probability p of y conditional on x. The network is a directed acyclic graph DAG, namely there are no cycles. The nodes and the arcs between the nodes define the structure of the network, and the conditional probabilities are the parameters given the structure. A simple example is given in Figure 16.1, which models that rain causes the grass to get wet. It rains on 40% of the days, and when it rains, there is a 90% chance that the grass gets wet. Maybe 10% of the time it does not rain, long enough for us to really consider the grass wet enough. The random variables in this example are binary. They are either true or false. There is a 20% probability that the grass gets wet without its actual raining, for example, when a sprinkler is used. So we see that these three values completely specify the joint distribution of P of RW. If P of R is equals to 0.4, then P of nut R is equals to 0.6. And similarly, P of nut W conditioning on R is equals to 0.1, and P of nut W conditioning on nut R is equals to 0.8. The joint is written as P of RW equals to P of R times P of W conditioning on R. And we can calculate the individual marginal probability of wet grass by summing up over the possible values that its parent node can take. That is, P of W equals to sigma summing for all P of RW summing for all R, which is equals to P of W conditioning on R times P of R plus P of W conditional on nut R times P of nut R, which is equals to 0.9 times 0.4 plus 0.2 times 0.6. That will be equals to 0.48. If we knew that it rained, the probability of wet grass would be 0.9. If we knew for sure that it did not rain, it would be as low as 0.2. Not knowing whether it rained or not, the probability is 0.4. So figure 16.1 shows a casual graph in that it explains that the cause of wet grass is rain. Bayes' rule allows us to invert the dependencies and have a diagnosis. For example, knowing that the grass is wet, the probability that it rained can be calculated as follows. P of R conditioning on W equals to P of W conditioning on R times P of R divided by P of W, which is equals to 0.75. And knowing that the grass is wet increased the probability of rain from 0.4 to 0.75. This is because P of W conditioning on R is high and the P of W conditioning on nut R is low. So we form graphs by adding nodes and arcs and generate dependencies. X and Y are independent events if P of xy is equals to P of x times P of y, and X and Y are conditionally independent events given a third event Z if P of xy conditioning on Z is equals to P of x conditioning on Z times P of y conditioning on Z, which can also be rewritten as P of x conditioning on y and z is equals to P of x conditioning on z. In a graphical model, Not all nodes are connected. Actually, in general, a node is connected to only a small number of other nodes. Certain subgraphs imply conditional independence statements, and these allow us to break down a complex graph into smaller subsets in which inferences can be done locally and whose results are later propagated over the graph. There are three canonical cases, and the larger graphs are constructed using these as subgraphs.